Hi, in this lecture and the coming lectures we are going to talk about the concrete implementation for the heap data structure. So I'm going to create two classes, the application from where we are going to test our data structure and a heap basically. So as we have discussed in a theoretical section, we are going to represent heap as a one-dimensional array. So I'm going to create a private integer. We are going to store integers in the heap data structure. It's going to have the name heap, okay? And we are going to have an index, the index of the current position. It's initialized to be -1 at the beginning. Okay, so in the heap constructor, we are going to get the size of the heap. So this dot heap is equal to a new integer, and the size is going to be the size we have specified from outside. Okay, so we have created basically a one-dimensional array of integers with the size we have specified. Okay, so I would like to implement the public void insert method. So I would like to insert a new item. Of course, we have to check that if is full, so if the data structure is full, of course we have to throw a new runtime exception with the message, for example, heap is full. Okay. Of course, we have to implement this isFull method. It's going to be a Boolean method, and it's going to return this dot current position is equal to the this dot heap dot length. So if we don't have any more space left, so any empty bucket basically in the one-dimensional array, it means that the heap is full, of course. And anyways, I would like to insert the given item to the next index possible. So I say that this dot heap with the index plus current position, I would like to increment the index to avoid collision. I would like to insert the item to the next position available. So it's going to be the item. Okay, then we have to fix up from the current position. What does it mean? That we have inserted a given item to the heap data structure, we have inserted it to the last position of the array, but sometimes it's not going to be a valid heap data structure. So as we have discussed in a theoretical section, we have the heap and we are going to have the indices 0, 1, 2, 3, 4, 5, 6, 7, 8. And that's why we are able to store the heap in a one-dimensional array. The root is going to be the first item, so with index 0, then 1 is going to be the left child of the root node, 2 is going to be the right child of the root node. So this is the basic relationship. The parent node with index I has a left child, 2 times I plus 1, it's going to be the index of the left child. The index of the right child will be 2 times I plus 2. And we keep inserting items to the next array slot possible. What does it mean? That we keep inserting items to the end of the heap data structure. It is a tree-like structure, okay, it's going to be valid, but sometimes the heap properties are going to be violated. So this is why if we insert, for example, 100, we have to check that, okay, for a maximum heap, the parent node should be greater than the left child or the right child. In this case, it's not going to be fine because 100 is greater than the parent, so we have to swap them. And basically, this is what we are going to do in the fix up method. We are going to check whether the heap properties are violated or not. So we have to get the parent index is equal to index -1 divided by 2. This is how we get the parent index for a given node. Okay, and we just have to say that while the parent index is greater or equal than 0 and this dot heap with the parent index is smaller than this dot heap with the index, what does it mean that the heap properties are violated? We are building a maximum heap, so the parent value should be greater, not smaller, than the heap at the given index. So while it is true, it means that this is not a valid heap. We have to swap the parent and the index. So we have a temp, it's going to be the heap with the given index. Then this dot heap with the given index is equal to the this dot heap with the parent index. Then this dot heap with the parent index is equal to the temp. We reinitialize the index to be equal to the parent index, and we set the parent index, of course, accordingly, because the index has changed. That's why we have to recalculate the parent index as well. Divide by 2. Okay, so what's happening? For example, we would like to insert 210. It's going to be the last item in the array, which means that it's going to be the right child of 5. This is the array representation of the heap. But as you can see, we have to make sure that, okay, whether it's going to be a valid maximum heap. No, because the maximum item is not in the root node. So we have to check that, okay, do we have to swap this item with the parent? Yeah, we have to swap it because this right child is greater than the parent. Okay, after swapping that, again we have to check whether this item is greater than the parent. And yeah, it is greater than the parent, so we have to swap them. So this is what's happening here. Why the parent index is greater than 0? What does it mean? That if we are at the root node, of course we don't have to make further iterations. And the heap parent index is smaller than the index. It means that the parent is smaller than the given item with the given index. So it means that it is not a valid maximum heap, so we have to swap them and we have to reinitialize the index accordingly. So this is how we implement insertion. Thanks for watching.